Hi, my name is Andy Morgan. I'm a science intern at NSF NOIRLab working with Stephanie Juno on machine learning methods for spectroscopic redshift estimation. So first, what is redshift? It's basically a cosmological distance attained by comparing the observed color of a spectral feature to its known intrinsic color. For example, I've marked the intrinsic color of the hydrogen alpha line with a small arrow on the left, and I've marked where we're actually observing it in this object with the arrow on the right. That feature, and in fact the entire spectrum, has been shifted redward. This is redshift, and we compare it with the cosmological expansion of the universe to derive cosmological distances. So not to go too deep into this, but redshifts are really important because they allow us to probe the nature of dark energy. Is it constant? Is it evolving? If it's evolving, is it speeding up or is it slowing down? So the traditional method for redshift estimation is called template fitting. We essentially try to reconstruct our input spectrum by linearly combining an assortment of rest frame feature templates at many different redshifts, and we look at which redshift produces the best reconstruction. Traditionally, these templates are derived from a relatively small number of objects with good observations and simulated data. They are not necessarily optimal or spanning of our full feature space, and as a result, they rely on a suite of algorithmic processing, post-hoc corrections, and ML-based afterburners that have become increasingly difficult to manage. Moreover, even with decades of accumulated experience and development, these methods are prone to failures that traditional templates simply have no way of intrinsically accounting for. Here's a plot showing disagreements between the two forefront spectroscopic redshift surveys, the Sloan Digital Sky Survey on the y-axis and the Dark Energy Spectroscopic Instrument on the x-axis, showing a few specific failure modes. Namely, there are line confusions, which are those labeled off-diagonal lines where two different distinct spectral features are confused for one another. There are template deficiencies, where the templates simply can't model certain objects or certain redshift ranges. And then there's contaminants like noise and cosmic rays, which are that diffuse cloud in the bottom left. Actually, getting to the machine learning, what can be done? The direct answer is machine learning optimized templates. So here I'm showing some templates learning directly from about 1 million spectra with known good redshifts. Their resultant reconstruction capability shown in that left-hand panel, and their redshift estimate shown in the right-hand panel. The beauty of this approach is that it's a direct translation of traditional methods into the language and world of machine learning. And it allows us to distill those decades of software development directly into the templates with no need for afterburners. So the templates shown here achieve sub% error rates all by themselves, and they can be trained to naturally account for confounding factors like line confusions, noise, and instrumentals through data augmentation. A more complementary method is probabilistic modeling to representation learning. That's a complex way of saying that we use a neural network to perform a fancy dimension reduction of our spectra. Then we learn a probability distribution over those representations for objects with known good redshifts. This lets us evaluate full probability distributions over redshift for each object, where we get point estimates, uncertainties, and we can examine degeneracies in a template-independent way. So here I'm showing a neural network actually learn that dimension-reduced representation colored by redshift. If we actually evaluate these posterior distributions to get point estimates, this is how they compare to their true redshifts, and it does very well. Every point on these plots actually is within 2 standard deviations of its true redshift, which means the points that are further off this one-to-one line are also intrinsically more uncertain. And we can even move past point estimates to do things like likelihood analyses to arbitrate those previously discussed survey disagreements. So on the left, the disagreements are arbitrated by actual humans looking at the spectrum. And on the right is simple arbitration by evaluating which redshift is more likely according to these learned distributions. And the important thing here is that these colors match up very closely. Additionally, we've also been able to show that we can implement this probabilistic model algorithmically in a single survey context to find and autonomously correct traditional pipeline errors without harm. So redshifts are important for understanding cosmology and the nature of the universe, but current methods are limited, monolithic, and it's difficult to know when they're wrong. We can address those first 2 points with machine learning optimized templates and techniques, and we can address that third point with robust probabilistic modeling. Thank you.